Picture the coastline of Southeast Asia, 50,000 years ago. A small group of humans stands at the water's edge, staring across a channel of open ocean. They can see land in the distance, a hazy outline on the horizon perhaps 60 miles away. They've never crossed water like this before. No human has. They have no boats, no sails, no navigation tools. They don't even have a word for ocean because they've never encountered one. Yet somehow, impossibly, they will make that crossing. And in doing so, they'll become the first humans to reach Australia, accomplishing a feat of exploration that wouldn't be matched for tens of thousands of years. This is one of the greatest mysteries in human prehistory. How did our ancestors cross vast stretches of ocean when they supposedly lacked the technology to do so? The evidence is undeniable. Humans reached Australia at least 65,000 years ago, possibly earlier. They colonized islands across the Pacific, reaching places like the Philippines, Japan, and eventually the remote islands of Oceania. Each of these journeys required crossing open ocean, sometimes dozens of miles of deep water with strong currents and no visible land on the other side. Yet archaeology finds no evidence of sophisticated boats from this early period. No ancient harbors, no depictions of vessels, no preserved hulls. So what happened? Did our ancestors possess boat-building skills far more advanced than we've given them credit for? Did they make desperate crossings on floating debris, drifting accidentally to new lands? Were sea levels so different that we're misunderstanding the geography entirely? Or is there something we're fundamentally missing about early human capabilities and their relationship with the sea? The answer challenges everything we thought we knew about our ancestors' intelligence, courage, and adaptability. Today, we're going to solve this mystery. We'll trace humanity's relationship with water from our earliest days in Africa to the astonishing ocean crossings that populated the globe. We'll examine the evidence, explore the theories, and ultimately discover that our ancestors were far more capable, far more daring, and far more ingenious than traditional archaeology has recognized. This is the story of how humans conquered the ultimate barrier, the open ocean. Chapter 1. Early voyagers. The first thing to understand is that humans have been interacting with water for far longer than most people realize. Our hominin ancestors weren't just savanna dwellers. Evidence from sites across Africa shows that early humans regularly inhabited lake shores, river valleys, and coastal areas. At a large assay in Kenya, sites dating back nearly 1 million years show evidence of humans living beside lakes, exploiting aquatic resources. These weren't just occasional visits. These were sustained occupations where water was central to daily life. Archaeological sites reveal that early humans were eating fish, shellfish, and other aquatic creatures hundreds of thousands of years ago. At Buklazi's river mouth in South Africa, caves occupied by anatomically modern humans around 100,000 years ago are filled with shells from mussels, limpets, and other marine mollusks. The humans living there weren't just opportunistically grabbing shellfish from tide pools. They were systematically harvesting marine resources, understanding tidal cycles, knowing when and where to find the best specimens. This requires sophisticated knowledge of the ocean's rhythms. But eating seafood doesn't require boats. You can wade into shallow waters, gather from rocks exposed at low tide, or spear fish in clear streams. The real question is when humans began deliberately constructing watercraft capable of carrying them beyond the shallows. Unfortunately, boats from this period have not survived. Wood, bark, and reeds, the materials ancient peoples would have used, decompose rapidly, especially in tropical and subtropical climates where early humans lived. We have stone tools lasting millions of years, but a wooden boat from 50,000 years ago? It's gone without a trace. This creates a fundamental problem for archaeology. The absence of evidence isn't evidence of absence. Just because we haven't found ancient boats doesn't mean they didn't exist. In fact, Indirect evidence strongly suggests that watercraft existed far earlier than the archaeological record shows. How else do we explain human presence on islands that were never connected to continents? How do we account for the spread of technologies and genetic markers across water barriers? The logical conclusion is that boats existed, but they simply haven't been preserved. The earliest direct evidence of watercraft comes from much later than the ocean crossings we're investigating. The oldest known boat is the Pes canoe from the Netherlands, dated to around 8000 BCE. It's a simple dugout canoe, made by hollowing out a pine log. Rock art from Scandinavia, dating to around 10,000 BCE, clearly depicts boats with multiple paddlers. Egyptian tomb paintings from 4000 BCE show sophisticated reed boats capable of carrying heavy cargo. But all of these are tens of thousands of years after humans had already crossed oceans. The boats we can see came long after the most impressive maritime journeys had already been accomplished. What would the earliest watercraft have looked like? Almost certainly, they were simple constructions. Logs lashed together to form rafts, bundles of reeds tied into boat shapes, animal skins stretched over wooden frames, hollow logs either naturally hollowed by decay or deliberately burned and scraped out. These are boats that anyone with Stone Age technology could construct, requiring only cutting tools, cordage, and understanding of basic principles. Modern experiments show that such craft are entirely seaworthy for coastal and even open ocean voyages. The Kon-Tiki expedition in 1947, though not a perfect analog, demonstrated that a balsa wood raft, using only materials and techniques available to ancient peoples, could cross the Pacific Ocean. Thor Heyerdahl and his crew sailed from Peru to Polynesia, covering over 4,000 miles. Later expeditions using reed boats similar to those depicted in ancient Egyptian art successfully crossed the Atlantic. These experiments prove that sophisticated naval architecture isn't necessary for ocean crossings. Simple watercraft, if properly constructed and handled, can accomplish remarkable journeys. But here's where it gets interesting. Humans might not have needed sophisticated boats for their earliest ocean crossings. The key is understanding that the ocean itself was different 50,000 years ago. Sea levels during the last ice age were dramatically lower than today, sometimes by 300 feet or more. This exposed vast areas of continental shelf that are now underwater. Coastlines extended miles beyond their current positions. Islands that seem isolated today were larger and closer together. Some were even connected by land bridges. The Sunda Shelf, connecting mainland Southeast Asia to islands like Sumatra, Java, and Borneo, was exposed during glacial periods, creating a vast subcontinent called Sundaland. Humans could have walked to these islands without ever getting their feet wet. Similarly, the Sahul Shelf connected Australia, New Guinea, and Tasmania into a single landmass called Sahul. What looks like impressive island hopping today was sometimes just walking across continuous land. The ocean crossings we read trying to explain may have been shorter and less daunting than modern geography suggests. However, even with lower sea levels, some water barriers remained. The strait between Sundaland and Sahul, known as Wallacea, was never completely closed. Even at the lowest sea levels, there were gaps of open ocean, some dozens of miles wide. The famous Wallace Line, identified by naturalist Alfred Russel Wallace, marks this permanent water barrier. Animals that spread throughout Sundaland never reach Sahul naturally, and vice versa. The fauna of Australia is radically different from Asia precisely because this water barrier prevented migration. Except for one species, us. Humans crossed the Wallace Line at least 65,000 years ago, probably earlier. Archaeological sites in northern Australia date to this period, and genetic evidence suggests that the initial colonization might have been even earlier. This crossing required traveling across open ocean, out of sight of land, probably multiple times to establish a viable population. It's arguably the greatest maritime achievement in human prehistory, accomplished by people who had never seen an ocean before, using technology that left no archaeological trace. How did they do it? Chapter 2. Island Colonization. The human arrival in Australia represents our species' first confirmed ocean crossing, but it's far from the only one. Archaeological evidence reveals that ancient humans were island hopping throughout Southeast Asia, reaching places that required deliberate maritime journeys. These weren't accidental drifts. They were purposeful expeditions, repeated multiple times, carrying enough people to establish viable populations. Understanding these journeys helps us comprehend the skills, technology, and daring of our ancestors. The Philippines provides fascinating evidence. The islands were never connected to mainland Asia, even during the lowest sea levels. Yet humans reached Luzon at least 67,000 years ago, as evidenced by the Kago cave remains. This required crossing at least 5 miles of open ocean from the nearest land, probably more depending on the exact route. The journey wasn't a one-time accident. Multiple crossings would have been necessary to maintain genetic diversity and establish a permanent population. These early Filipinos were accomplished seafarers. Even more impressively, they reached remote islands within the Philippine archipelago. Excavations on various islands reveal human presence dating back tens of thousands of years. Each island required a separate voyage. The distribution of artifacts and human remains shows that these weren't isolated castaways clinging to survival. These were thriving communities, trading between islands, developing distinct cultures, and successfully adapting to island environments. They were, in effect, running a maritime network across dozens of islands without any of the navigation technology we consider essential today. Japan's initial human colonization also required water crossings. The Japanese islands were never fully connected to mainland Asia, though the straits were narrower during glacial periods. Archaeological evidence places humans in Japan at least 38,000 years ago. The strait between Korea and Japan, at its narrowest point, is about 30 miles wide. Even under the best conditions, this represents a serious maritime challenge. Yet ancient humans made this crossing, bringing with them their tools, knowledge, and presumably, the skills necessary to return or send other expeditions. The Mediterranean islands show similar patterns. Crete, for example, has stone tools dated to at least 130,000 years ago, far earlier than previously thought possible. Crete has been an island for millions of years, separated from mainland Greece by deep channels at least 40 miles wide. The presence of these ancient tools proves that pre-modern humans, possibly Neanderthals or even earlier hominins, were capable of open ocean crossings far earlier than anyone suspected. This discovery fundamentally challenges our understanding of ancient maritime capabilities. Cyprus provides another intriguing case. The island shows evidence of human visitation around 12,000 years ago, with permanent settlement beginning around 10,000 years ago. Cyprus was never connected to the mainland, requiring a sea voyage of at least 40 miles. Early settlers brought domesticated plants and animals, meaning they were making planned expeditions, not accidental voyages. You don't accidentally drift to an island while carrying seeds, goats, and pigs. These were deliberate colonization missions, carefully planned and executed. The Ryukyu Islands, stretching from Japan toward Taiwan, were settled at least 30,000 years ago. These islands form a chain with some segments requiring significant water crossings. The humans who settled them developed a distinct culture, adapting to island life while maintaining some connections to mainland populations. The discovery of similar tool types across the island chain suggests regular contact, meaning people were routinely crossing between islands, not just making one-way journeys. What motivated these journeys? Why risk crossing open ocean to reach unknown lands? One answer is curiosity and adventure. Humans are naturally exploratory. We see a horizon and want to know what's beyond it. But there are also practical reasons. Population pressure might drive groups to seek new territories. Resource depletion could make migration necessary. Following game animals or bird migrations might lead people to discover islands. Climate changes could make current territories less habitable, encouraging exploration of new options. Another possibility is that visible signs indicated land beyond the horizon. Smoke from fires, whether natural or man-made, can be seen from great distances. Cloud formations often form over islands, visible from far away. Birds flying in consistent directions, particularly at dawn and dusk, indicate land. Ancient peoples, intimately familiar with their environment, would recognize these signs. They wouldn't be sailing blindly into empty ocean. They'd have reasonable confidence that land existed in a particular direction. The crossings themselves probably used simple watercraft, rafts, reed boats, or dugout canoes. Multiple boats would travel together, providing backup if one failed and carrying enough people to establish a viable population. They'd wait for favorable weather, calm seas and steady winds in the right direction. They'd bring water in containers, probably gourds or animal skins. Food would include dried meat, fish, and gathered plant foods. These provisions would sustain them for the days necessary to complete the crossing. Navigation would rely on natural cues. The sun's position indicates direction during the day. Stars, particularly the fixed position of Polaris in the northern hemisphere or the Southern Cross in the southern, provide nighttime orientation. Wave patterns and ocean swells have consistent directions influenced by prevailing winds. Experienced seafarers learn to read these subtle signs. Birds, clouds, and even the smell of land carried on the wind provide information. Ancient navigators developed sophisticated mental maps of their maritime world, passing this knowledge through oral tradition and practical training. The risks were enormous. Storms could swamp small craft. Strong currents could carry boats far off course. Dehydration and exposure could kill. Many expeditions probably ended in disaster, with boats lost at sea and crews drowned. But enough succeeded to populate dozens of islands across the Indo-Pacific. The humans who accomplished these crossings were skilled, brave, and determined. They expanded human territory beyond any previous boundary, proving that even the ocean couldn't contain our species' expansive drive. Chapter 3. Continental migrations while island hopping in Southeast Asia and the Pacific demonstrates impressive maritime capability. It pales in comparison to some of the truly staggering ocean crossings that ancient humans accomplished. These journeys challenge our understanding of what was possible with Stone Age technology and raise profound questions about how they were achieved. Some remain controversial, with archaeologists debating whether the evidence supports intentional voyages or accidental drifts. But the human presence is undeniable. The colonization of Sahul, the combined landmass of Australia, New Guinea, and Tasmania during the Ice Age, represents humanity's most ancient confirmed ocean crossing. The earliest evidence places humans in northern Australia at least 65,000 years ago, though some researchers argue for dates as early as 80,000 years ago based on genetic evidence and controversial archaeological finds. These dates push human maritime capability back to a time when our species had barely left Africa, suggesting that seafaring developed very early in modern human evolution. The journey from Sunderland to Sahul required crossing the Wallacea region, a stretch of ocean that remained even when sea levels were at their lowest. The exact route is debated, but all possibilities involve crossing significant stretches of open water. The northern route, from Sulawesi or nearby islands to New Guinea, involves multiple water gaps, the longest being about 60 miles. The southern route, from Timor to northern Australia, crosses a single gap of perhaps 50 miles. Either way, these are serious maritime undertakings, especially for first-time ocean crossers. What makes this achievement even more remarkable is that it wasn't a one-time lucky accident. Genetic studies show that the initial population that colonized Sahol numbered at least several hundred individuals, possibly more. This means multiple successful voyages, each carrying dozens of people, or fewer voyages carrying very large groups. Either scenario requires watercraft capable of carrying many people safely across open ocean. We're not talking about someone clinging to driftwood and washing ashore by chance. These were organized expeditions. The colonizers brought technology and knowledge with them. Within a few thousand years of arrival, they had spread across the entire Australian continent, adapting to environments ranging from tropical rainforests to arid deserts. They developed sophisticated tool traditions, created some of the world's oldest rock art, and established complex social and spiritual systems. This wasn't a group of desperate castaways barely surviving. These were capable, organized people who chose to cross an ocean and succeeded spectacularly. Madagascar's human colonization presents an even more puzzling case. The island lies off the east coast of Africa, separated by the Mozambique Channel, which is about 250 miles wide at its narrowest point. Yet humans didn't reach Madagascar from nearby Africa. Instead, the first colonizers arrived from Southeast Asia, specifically from Borneo or nearby regions, around 2,000 years ago. They traveled over 4,000 miles across the Indian Ocean, one of the most impressive maritime journeys in human prehistory. How did Austronesian peoples from Indonesia reach Madagascar? The most likely explanation involves intentional voyaging using sophisticated outrigger canoes. By 2,000 years ago, Austronesian cultures had developed advanced maritime technology, including outriggers for stability, sails for propulsion, and accumulated navigation knowledge from centuries of island colonization across Southeast Asia and the Pacific. They were arguably the world's greatest seafarers, and their journey to Madagascar, while extreme, was within their capabilities. But why would they make such a journey? The distance is staggering, and there's no evidence they knew Madagascar existed before reaching it. One theory suggests they were trading along the East African coast and gradually worked their way south, eventually discovering the island. Another possibility is that they were following seasonal wind patterns across the Indian Ocean, possibly in stages, using islands along the way. Some researchers even suggest accidental drift, with boats blown off course during monsoon seasons eventually reaching Madagascar. The truth remains uncertain, but the achievement is undeniable. The Pacific Islands present the most extensive evidence of ancient ocean crossings. Austronesian peoples, originating from Taiwan around 5,000 years ago, spread throughout the Pacific in a diaspora that reached Hawaii, Easter Island, and New Zealand. These journeys required crossing thousands of miles of open ocean, often with no land visible for days or weeks. They carried domesticated plants and animals, establishing agricultural communities on remote islands. This was clearly planned colonization, not accidental drift. The Polynesian navigators who accomplished these crossings used sophisticated wayfinding techniques passed down through generations. They memorized star paths, observing which stars rose and set at particular points on the horizon throughout the year. They read wave patterns, detecting subtle changes that indicated land or changes in currents. They observed birds, knowing that certain species only flew within specific distances from land. They carried mental maps of entire ocean regions, encoded in chants and stories that preserved navigational knowledge. Their canoes were technological marvels. Large double-hulled vessels, sometimes over 70 feet long, could carry dozens of people along with supplies, animals, and plants. Outriggers provided stability. Sails, woven from pandanus or other plant fibers, harnessed the wind. These weren't primitive craft. They were sophisticated vessels designed through centuries of accumulated experience. Modern reconstructions, built using traditional techniques, have successfully replicated ancient Polynesian voyages, proving that these journeys were entirely feasible. But what about earlier crossings, before this sophisticated technology existed? How did humans reach Australia 65,000 years ago, or the Philippines even earlier? The watercraft must have been simpler: rafts, reed boats, or basic dugouts. Yet they succeeded in crossing significant stretches of ocean. This suggests that while the technology was simple, the people using it were highly skilled. They understood water, weather, and navigation intimately. They were patient, waiting for optimal conditions. They were brave, willing to risk the unknown. And they were numerous enough that even with high failure rates, some expeditions succeeded. Some researchers argue that accidental drift explains some early island colonizations. Storms could blow fishing boats far out to sea. People on rafts or simple boats, carried by currents, might reach distant shores. Pregnant women in these groups could establish new populations. While this can't be entirely ruled out, it seems insufficient to explain the patterns we see. The distribution of human populations across islands, the genetic evidence of substantial founding populations, and the successful adaptation to new environments all suggest that most colonizations were deliberate, not accidental. Chapter 4. DNA Stories. DNA tells a story that archaeology alone cannot. While we may never find the boats ancient humans used to cross oceans, we can trace their journeys through genetic markers passed down through generations. Modern genetic studies reveal the pathways ancient peoples took, how many individuals were involved, and even approximately when these journeys occurred. The evidence confirms what artifacts suggest. Humans were crossing oceans far earlier and more frequently than once believed possible. Mitochondrial DNA passed from mothers to children, and Y chromosome DNA passed from fathers to sons, act like molecular clocks. Mutations accumulate at relatively predictable rates, allowing geneticists to estimate when populations diverged. By comparing DNA from modern populations across different regions, researchers can reconstruct ancient migration patterns. Australian Aboriginal populations, for example, show genetic signatures indicating arrival on the continent at least 65,000 years ago, consistent with archaeological evidence. The genetic data reveals something remarkable. The founding population that reached Sahul was quite large, probably several hundred individuals at minimum. This isn't what you'd expect from accidental drift or a single lucky boat. It suggests organized migration, multiple crossings, or very large boats carrying substantial numbers of people. The genetic diversity of Aboriginal Australians, while less than African populations, is still considerable, indicating that the founders weren't a tiny bottleneck, but a reasonably sized group. Island populations throughout Southeast Asia show similar patterns. Genetic studies of populations in the Philippines, Andaman Islands, and other isolated locations reveal founding events tens of thousands of years ago. Each island population carries distinctive genetic markers that trace back to these ancient colonizations. The patterns show that these weren't just explored territories, but settled lands where populations grew and thrived. The genetic evidence confirms sustained maritime activity going back deep into prehistory. The Austronesian expansion across the Pacific is particularly well documented genetically. Populations from Taiwan, the Philippines, Indonesia, and across Oceania share genetic markers indicating common ancestry. The trail of genetic breadcrumbs traces the voyaging routes these ancient mariners followed, island by island, across the Pacific. But the genetics also reveal interbreeding with earlier populations, including Denisovans in Southeast Asia and possibly other archaic humans. This shows that the voyagers didn't simply replace existing populations, but sometimes integrated with them. Madagascar's settlement story becomes even more intriguing through genetics. The Malagasy people show a roughly 50-50 genetic mix of Southeast Asian and East African ancestry. This confirms that settlers from Indonesia mixed with African populations, probably along the East African coast, before or during the colonization of Madagascar. Some genetic evidence suggests multiple waves of migration from both regions. The maternal lineages are predominantly Southeast Asian, while paternal lineages show more African influence, suggesting complex population dynamics. Denisovan DNA in modern populations provides evidence of ancient ocean crossings. Denisovans, a sister species to Neanderthals, inhabited parts of Asia and apparently reached some islands. Modern Melanesians, Aboriginal Australians, and Philippine Negritos carry significant Denisovan ancestry, sometimes 4 to 5% of their genome. This Denisovan DNA includes genetic variants that help these populations adapt to island environments, including immune system genes and genes affecting metabolism. The presence of Denisovan DNA in island populations proves that either Denisovans themselves crossed water barriers, or early modern humans encountered Denisovans on islands they reached. The genetic evidence also reveals isolation and connectivity patterns. Some island populations show extreme isolation, with little genetic exchange with other groups for thousands of years. The Andaman Islanders, for example, remain genetically isolated for perhaps 60,000 years until recent contact. Other populations show evidence of ongoing contact, with genetic exchange continuing over millennia. This pattern suggests that while some ocean crossings were one-way journeys to isolated refuges, others were part of ongoing maritime networks. Ancient DNA, extracted from archaeological remains, provides direct evidence of prehistoric populations. Remains from Australia, dating back several thousand years, show genetic continuity with modern Aboriginal populations, confirming that current inhabitants are descendants of the original colonizers. Ancient DNA from Pacific Islands traces the Austronesian expansion, showing how populations moved from island to island. Each ancient genome is like a snapshot of a moment in human history, revealing who lived where and when. Genetic evidence even sheds light on individual voyages. The colonization of Polynesia, for instance, shows founder effects where small groups established new island populations. The genetic markers in Hawaii, Easter Island, and New Zealand indicate that each was settled by relatively small founding groups, probably one or a few canoe loads of people. Yet these tiny populations succeeded in establishing thriving civilizations, demonstrating the hardiness and adaptability of these ancient voyagers. The combination of mitochondrial DNA, Y chromosome markers, and autosomal DNA paints a complex picture. Maternal and paternal lineages sometimes tell different stories, suggesting that men and women may have had different migration patterns. Some colonizations show predominantly male or female founders, indicating that the composition of voyaging groups varied. These details help us understand not just where humans went, but how they organized their expeditions and what social structures they maintained. Genetics also reveals failed colonizations. Some islands show evidence of early human presence that later disappeared, only to be recolonized thousands of years later. The genetic signature shows distinct founding events, meaning the earlier population died out completely. This sobering evidence reminds us that not all voyages ended in success. Environmental challenges, limited genetic diversity, or catastrophes could wipe out small, isolated populations. For every successful colonization, there may have been multiple failures we'll never know about. The genetic clock continues ticking. As populations evolve in isolation, they accumulate unique mutations. The number and type of these mutations help determine how long populations have been separated. Aboriginal Australian populations show some of the deepest genetic divergences outside Africa, confirming their long isolation. Island populations throughout Oceania show divergence proportional to their distance and isolation, with the most remote islands showing the most distinctive genetic profiles. Modern genetic studies are revolutionizing our understanding of human maritime history. They confirm that ocean crossings occurred far earlier than boats in the archaeological record would suggest. They show that these crossings involved substantial numbers of people, not just lucky accidents. They trace the routes ancient peoples followed across oceans, and they demonstrate that our ancestors were bold, capable seafarers who conquered Earth's ultimate barrier not once, but repeatedly, expanding human territory to every habitable land on the planet. Chapter 5. Vanished Boats. One of the most frustrating aspects of studying ancient maritime history is the near-total absence of watercraft in the archaeological record. Wood rots, reeds decompose, and even stone anchors can be difficult to identify with certainty. We're left trying to understand sophisticated capabilities from almost no physical evidence. But the absence of artifacts doesn't mean absence of technology. It means we need to think differently about what ancient peoples could accomplish and how they did it. Consider what watercraft requires at its most basic level, something that floats and can be controlled. Logs float naturally and can be ridden or pushed. Bundle enough logs together, and you have a raft capable of carrying people and cargo. This requires only the ability to cut wood and create cordage for lashing. Both capabilities existed hundreds of thousands of years ago. Stone tools can fell trees and shape wood. Plant fibers, animal sinews, or strips of hide create cordage. The basic technology for watercraft existed long before humans reached Australia. Reed boats represent another simple technology with ancient roots. Reeds, particularly papyrus and similar water plants, are naturally buoyant. Bundle them tightly into boat shapes, and they form watercraft that can last months or even years if properly maintained. Ancient Egyptians used reed boats for thousands of years, depicted in tomb paintings and described in texts. Modern experiments with reed boats, like Thor Heyerdahl's expeditions, proved they're capable of ocean crossings. Ancient peoples living near wetlands or rivers would have naturally discovered reed's buoyancy. Dugout canoes require more sophisticated technology, but were certainly within ancient capabilities. A single large log, hollowed through a combination of fire and scraping, becomes a stable, durable boat. Archaeological evidence places dugout canoes at least 10,000 years old, but the technique could be far older. Fire-based woodworking is ancient, with evidence going back hundreds of thousands of years. Once you can control fire and work wood, dugout canoes become feasible. They're time-consuming to make, but last years and can be quite large. Bark canoes represent another option. Indigenous Australians and many other cultures constructed excellent boats from tree bark, particularly eucalyptus and birch. Large sheets of bark, carefully removed from trees, can be shaped into canoes while still pliable. The seams are sealed with natural resins. The resulting craft are lightweight, durable, and quick to construct compared to dugouts. Bark canoes leave almost no archaeological trace, decomposing rapidly, but they were widespread in recent indigenous cultures and likely have ancient roots. Skin boats, like kayaks and coracles, use animal hides stretched over wooden frames. These boats are lightweight, tough, and highly seaworthy. Modern reconstruction of ancient designs shows that skin boats can handle remarkably rough conditions. Arctic peoples used kayaks for ocean hunting for thousands of years. The Irish used hide-covered carracks for ocean voyages. The Mongols used similar boats to cross rivers during their conquests. Skin boats could certainly be ancient, requiring only hides, cordage, and basic framework construction. Outriggers represent a crucial innovation in boat stability. A single log or narrow hull is unstable, tipping easily. But add an outrigger, a float connected by spars extending from one or both sides, and the boat becomes remarkably stable. Polynesian outrigger canoes could carry dozens of people and cargo across thousands of miles of ocean. The technology is simple in concept, but represents a significant intellectual leap. Someone had to conceive of using a secondary float for stability. Once invented, the idea spread rapidly throughout maritime cultures. Sails transformed watercraft from muscle-powered to wing-powered vessels. The earliest sails were probably simple mats of woven plant fiber or animal skins held up to catch the wind. Even crude sails dramatically increase range and speed, allowing boats to travel distances impossible with paddling alone. Polynesians used sophisticated sail designs, including crab claw sails that could tack into the wind. Egyptian tomb paintings show fully developed sailing vessels by 3000 BCE, but simpler sails could be far older. What about navigation technology? Ancient mariners probably used simple tools we wouldn't recognize as navigation instruments. A stick or bone with marks indicating star positions could serve as a memorization aid. Shells or stones arranged in patterns could represent island positions and sailing directions. Stories and chants encode navigational information in memorable forms. Polynesian navigation schools trained students for years, teaching them to recognize hundreds of star positions, wave patterns, and environmental cues. The technology was mostly mental, leaving no archaeological trace. Water containers were essential for any significant voyage. Without fresh water, ocean crossings lasting more than a day or two become impossible. Gourds, which dry into durable, waterproof containers, grow naturally throughout tropical regions. Animal bladders and stomachs, properly cleaned and sealed, hold water. Later cultures used ceramic vessels, but organic containers served long before pottery was invented. Evidence for container use goes back tens of thousands of years, making water storage technology available for ancient voyages. Provisioning for voyages required food preservation techniques. Drying meat and fish prevents spoilage, creating rations that last weeks or months. Smoked foods last even longer. Nuts, seeds, and dried fruits provide calories and nutrients. Indigenous cultures worldwide developed sophisticated food preservation methods using only Stone Age technology. Ancient mariners undoubtedly used similar techniques, carrying provisions for journeys lasting days or weeks. Celestial navigation requires no technology beyond knowledge and observation. The North Star, or Southern Cross in the Southern Hemisphere, provides fixed direction points. The sun's position indicates east and west, rising and setting at predictable points that vary by season and latitude. Experienced navigators learn these variations, using the sun's arc to estimate latitude. Star paths, the rising and setting points of specific stars throughout the year, provide precise directional information. All of this requires only memory and practice. Wave and swell patterns provide information about land and weather. Waves reflect off islands, creating interference patterns detectable by experienced seafarers. Swells, long-period waves generated by distant weather systems, maintain consistent directions over hundreds of miles. By reading swells, navigators determine direction even under cloudy skies when celestial navigation is impossible. This technique requires no instruments, only trained perception and understanding of ocean dynamics. Birds indicate land proximity. Different species range different distances from shore. Seeing land birds means shore is within their range, usually 50 to 100 miles depending on species. Birds flying in consistent directions, particularly at dawn and dusk, fly toward land where they roost. Following birds is a reliable way to find islands. Ancient mariners certainly knew this, using birds as natural navigation aids. Cloud formations reveal distant land. Clouds form over islands due to rising warm air. From sea level, these clouds are visible long before the island itself appears over the horizon. The color of clouds can also indicate land, reflecting green from vegetation or pale from sandy beaches. The underside of clouds over lagoons reflects turquoise. Experienced mariners read clouds like signposts. detecting islands from great distances. The technology of ancient seafaring was simple but effective, relying more on knowledge, skill, and experience than on sophisticated equipment. The boats were basic but seaworthy. The navigation used natural cues rather than instruments. The provisions were simple but adequate. What appears primitive to us was actually a complete maritime system, developed through generations of experience, fully capable of accomplishing what the evidence proves they did, crossing oceans and colonizing islands throughout the ancient world. Chapter 6. Polynesian Navigators. If ancient humans crossing to Australia 65,000 years ago was impressive, the Polynesian expansion across the Pacific Ocean 3,000 years ago was extraordinary. The Austronesian peoples, originating from Taiwan around 5,000 years ago, embarked on the greatest expansion in human prehistory, spreading across an area larger than all land continents combined. They settled virtually every habitable island in the Pacific, from Papua New Guinea to Easter Island, from Hawaii to New Zealand. This achievement required sophisticated maritime technology, advanced navigation skills, and remarkable courage. The story begins in Taiwan, where the Austronesian language family originated. Around 3000 BCE, people speaking Proto-Austronesian languages began moving south into the Philippines and Indonesia. They brought with them agriculture, particularly rice and millet cultivation, domesticated animals including pigs and chickens, and crucially, advanced canoe technology. These were not simple dugouts, but sophisticated outrigger canoes, capable of carrying substantial cargo and passengers across open ocean. By 1500 BCE, Austronesian peoples had reached the islands of Melanesia, including the Bismarck Archipelago and Solomon Islands. Here they encountered, and sometimes mixed with existing populations, descended from the ancient Sahul colonizers. The genetic and cultural mixing created new populations, but the Austronesian maritime tradition continued. They kept pushing eastward into the remote Pacific, reaching islands no human had ever seen. Around 1000 BCE, these voyages reached Fiji, Tonga, and Samoa, establishing the Lapita culture, named after a distinctive pottery style. The Lapita people were master mariners and skilled potters who created elaborate decorated ceramics. Their settlements spread across hundreds of islands, maintaining communication and trade across vast ocean distances. The Lapita expansion represents one of the most rapid and extensive colonization events in human history, covering an area from the Bismarck Archipelago to Samoa in just a few centuries. After a pause of perhaps 1,000 years, the expansion resumed even more dramatically. Polynesian navigators, descendants of the Lapita culture, pushed into the remote eastern Pacific. They reached the Marquesas Islands around 300 CE, then spread to Hawaii by about 400 CE, Easter Island by 800 CE, and finally New Zealand by 1200 CE. These journeys involved crossing thousands of miles of open ocean, often with no land visible for weeks. Easter Island, the most remote inhabited island on Earth, lies over 1,200 miles from the nearest other island. Reaching it required extraordinary navigation skills and iron determination. The voyaging canoes that accomplished these feats were technological marvels. The largest were double-hulled vessels, with two parallel hulls connected by a platform. This design provided stability in rough seas and created a large deck area for cargo and passengers. Some vessels exceeded 70 feet in length and could carry 50 or more people, along with provisions, animals, and plants. The hulls were constructed from planks sewn together with coconut fiber cordage, caulked with breadfruit sap or other natural resins. No metal was used. Everything was stone, bone, or plant materials. The sails were equally impressive. Woven from pandanus leaves or other plant fibers, they could be raised, lowered, and adjusted to harness winds from various directions. The distinctive oceanic crab claw sail, with its curved spars forming a triangular shape, was particularly efficient. It could be quickly adjusted and even allowed some degree of sailing into the wind, a crucial capability for exploration. The sails weren't just functional. They were often decorated with complex patterns, serving as clan identifiers and status symbols. Navigation was where Polynesian maritime culture truly excelled. Navigators trained for years, learning vast amounts of information passed down through generations. They memorized star compasses, mental constructs dividing the horizon into segments marked by rising and setting points of specific stars. Different stars occupied these positions throughout the year, so navigators learned seasonal variations. They could maintain course by keeping particular stars at specific positions relative to the canoe, adjusting as different stars rose and set through the night. Wave patterns provided another crucial navigation tool. The ocean isn't random chaos, but organized patterns of waves and swells from different sources. Navigators learned to identify the deep swells generated by distant storms, maintaining consistent directions across hundreds of miles. They detected the interference patterns where swells reflected off islands, perceiving these changes through the canoe's motion. Some navigators could detect islands from 50 miles away by reading wave patterns, feeling subtle changes invisible to the untrained. Island navigation involved understanding whole ocean systems. Navigators knew that certain islands lay on specific bearings from their home, that star paths led to particular destinations, that seasonal winds enabled certain voyages while making others dangerous. This knowledge was organized into complex mental maps, often encoded in chants and stories that served as mnemonic devices. The information was taught in navigation schools, with students spending years learning before being trusted to guide voyages. The expansion wasn't random exploration. Evidence suggests deliberate, planned voyages of colonization. The Polynesians carried with them a transported landscape, a suite of domesticated plants and animals to establish on new islands. They brought taro, yams, breadfruit, coconuts, bananas, chickens, pigs, and dogs. They brought women, children, and elders, not just young male explorers. They carried enough people to establish viable populations. This level of planning proves these were intentional colonization expeditions, not accidental discoveries. How did they know where to go? Some islands might have been discovered accidentally by fishing boats blown off course or damaged in storms. But returning to report the discovery and then organizing colonization expeditions required accurate navigation. More likely, deliberate exploration voyages searched for new lands. Birds flying to distant feeding grounds might indicate islands beyond the horizon. Cloud formations could reveal land from great distances. Navigators might have sailed in specific directions, using seasonal wind patterns that would carry them outward and then reverse to bring them home. The voyages could take weeks or months. Provisions included dried fish, fermented breadfruit paste, coconuts for both food and water, and collected rainwater. Fishing from the canoe supplemented supplies. The crew would take turns sleeping and sailing, maintaining watches throughout the voyage. In calm conditions, they might drift, conserving energy. In favorable winds, they'd push hard to make maximum progress. The physical and psychological challenges were immense, yet these voyages succeeded repeatedly. New Zealand's colonization, the last major expansion, represents perhaps the ultimate achievement. The journey from central Polynesia to New Zealand covered over 2,000 miles across challenging southern oceans. The climate was far colder than tropical islands Polynesians were accustomed to. Yet they successfully established populations that became the Maori people, adapting their tropical agricultural systems to temperate conditions. Within a few centuries, they had explored and settled both main islands of New Zealand, developing a distinct culture while maintaining core Polynesian traditions. The Polynesian expansion raises profound questions about return voyages. Did canoes regularly travel back and forth between island groups? Some evidence suggests yes. Sweet potatoes, native to South America, appear in Polynesia before European contact, proving that Polynesian navigators reached South America and returned. Genetic evidence shows limited but definite contact between Polynesian and South American populations around 1200 CE. This means Polynesians crossed over 2,000 miles of open Pacific Ocean to South America, made contact with indigenous peoples, acquired sweet potatoes, and returned to Polynesia to introduce the crop. The extent of the Polynesian maritime network remains debated. Did islands maintain regular contact, or were many colonized by one-way voyages followed by isolation? The evidence shows both patterns. Some islands show genetic and cultural evidence of ongoing contact with other populations. Others, particularly the most remote like Easter Island and Hawaii, became isolated after initial settlement, developing unique cultures. New Zealand, despite its distance, shows evidence of return knowledge to central Polynesia, with traditions remembering the homeland of Hawaii. The Polynesian expansion eventually reached its limits. Every habitable island in the vast Pacific was discovered and settled. There simply were no more islands to find. The voyaging tradition gradually declined as the age of exploration ended, though inter-island navigation continued. By the time Europeans arrived in the Pacific in the 16th century, the Great Expansion was long over, but the navigational knowledge remained in some island groups, particularly in the Carolines of Micronesia, where traditional navigation survived into modern times. Modern revival efforts have rediscovered traditional navigation techniques. In 1976, the double-hulled canoe Hakole sailed from Hawaii to Tahiti using only traditional navigation, no modern instruments. The successful voyage, guided by Micronesian navigator Mo Pialag, proved that ancient techniques remained viable. Since then, Hakole and other voyaging canoes have sailed throughout the Pacific, training new generations in traditional wayfinding. These voyages demonstrate conclusively that Polynesian ancestors could have, and did, accomplish what archaeological and genetic evidence proves they did. The Polynesian expansion stands as humanity's greatest maritime achievement prior to European oceanic exploration. Without metal tools, without compasses or charts, without writing to record knowledge, Polynesian navigators mapped an ocean larger than all continents combined. They discovered and settled every habitable speck of land. They maintained knowledge systems preserving navigational information across generations. They created a maritime culture unmatched in human history. And they did it all using wooden canoes, woven sails, and their own remarkable intelligence, courage, and skill. The Polynesian expansion represents not just an impressive maritime achievement, but arguably the greatest feat of exploration and navigation in human history, before the European age of discovery. To fully appreciate what Polynesian navigators accomplished, we must understand the sheer scale, the sophisticated techniques, the cultural systems that supported voyaging, and the profound courage required to sail into unknown waters with no guarantee of return. These were not accidental drifts or lucky discoveries, but deliberate, planned expeditions executed with remarkable skill and precision. The training of a Polynesian navigator was rigorous and began in childhood. In societies where navigation knowledge was sacred and powerful, not everyone could become a navigator. The training was typically restricted to certain families or social classes, with knowledge passed from master to apprentice over many years. Young students learned through a combination of formal instruction, practical experience, and memorization of vast amounts of information encoded in chants, stories, and physical models. The education could take a decade or more before a student was trusted to navigate independently. Navigation schools existed on various islands, with the most famous being the schools in the Caroline Islands of Micronesia, where traditional navigation survived into modern times and provided insights into ancient Polynesian methods. Students learned to recognize hundreds of stars and their rising and setting points throughout the year. They memorized star paths, sequences of stars that would guide voyagers to specific destinations. They learned to feel wave patterns through the motion of the canoe, detecting subtle changes that indicated land, currents, or weather changes. They studied cloud formations, bird behavior, ocean colors, and countless other environmental cues. The star compass was a mental construct, not a physical instrument, dividing the horizon into segments marked by the rising and setting points of specific stars. Different islands used different numbers of segments, some with as few as 16, others with 32 or more. Navigators memorized which stars rose and set in which segment at different times of year. By keeping a particular star at a specific position relative to the canoe, they maintained course. When that star rose too high or set, they switched to another star in the same position. Through the night, they worked through a sequence of stars, maintaining consistent direction. During daylight hours, the sun provided directional information. Its rising and setting points vary with the seasons, moving north and south along the horizon throughout the year. Experienced navigators knew these variations and could estimate direction from the sun's position. The sun's arc across the sky also indicated approximate latitude, rising higher overhead near the equator and lower toward the poles. At noon, the sun's height provided rough latitude estimates, though Polynesian navigators didn't think in terms of degrees, but rather in terms of star islands and other culturally specific concepts. Wave and swell patterns provided crucial information, especially at night or during overcast conditions when celestial navigation was impossible. The Pacific Ocean features several major swell systems generated by storms in different regions. These swells maintain consistent directions over thousands of miles, creating a kind of oceanic compass. Navigators learned to distinguish different swells by their period, the time between wave crests, and their direction. By feeling the motion of the canoe as it rode different swells, a skilled navigator could maintain course even without seeing sky or stars. Island detection from great distances was crucial for successful voyaging. Polynesian navigators developed multiple techniques for detecting land before it became visible. Clouds often form over islands due to rising warm air, visible from much farther away than the island itself. The color and shape of clouds provided information about island size and terrain. Lagoon reflections on the underside of clouds created distinctive turquoise glows. Stationary clouds in otherwise moving skies often indicated land beneath them. Birds served as living signposts pointing toward land. Different species ranged different distances from shore, so seeing certain birds indicated proximity to land. Noddies and terns typically stayed within 30 to 40 miles of land, while frigate birds ranged somewhat farther. Most importantly, birds flying in consistent directions, particularly at dawn and dusk when they commuted between feeding and roosting areas, pointed toward land. A skilled navigator seeing birds at dusk flying toward the northeast knew that land lay in that direction, probably within a day's sailing. Ocean color changes indicated approaching land. Deep ocean is deep blue or purple, while shallower waters near islands appear lighter blue or green. This color change becomes visible miles before the island itself. The smell of land, carried on the wind, could be detected from surprising distances, especially if the island had vegetation or if smoke from fires drifted seaward. Navigators developed acute sensitivity to these subtle environmental cues, reading information from the ocean that would be invisible to untrained observers. The physical construction of voyaging canoes involved sophisticated engineering and represented the accumulated knowledge of generations. The largest double-hulled canoes were monumental projects requiring months or years of work by specialized craftspeople. The hulls were carved from enormous trees, requiring finding, felling, and transporting logs that might weigh several tons. In islands lacking large trees, hulls were built up from planks sewn together with braided coconut fiber cordage. The planking technique required precise shaping so planks fit together tightly, then drilling holes along the edges for sewing, and finally caulking seams with breadfruit sap or other natural adhesives. The two holes were connected by crossbeams lashed to the gunnels, with the lashing itself being an art form involving complex patterns that distributed stress and allowed some flexibility. The platform created between the hulls provided space for crew, supplies, and cargo. Some vessels included a small shelter or house on this platform to protect passengers from sun and spray. The entire structure had to be strong enough to withstand the forces of ocean sailing, yet light enough to achieve reasonable speed. The engineering represented centuries of experimentation and refinement. Sails were woven from pandanus leaves, a labor-intensive process involving harvesting leaves, drying them, stripping the tough fibers, and weaving them into large mats. A sail for a large voyaging canoe might take months to complete and required hundreds of pandanus leaves. The weaving had to be tight enough to catch wind, but flexible enough to adjust to changing conditions. The crab claw sail design, shaped like an inverted triangle with curved spars, was particularly effective. It could be quickly adjusted by rotating it around the mast, allowing the canoe to sail at various angles to the wind. The steering paddle or oar was another crucial element, requiring skill to operate effectively. Unlike modern rudders that turn to change direction, Pacific steering paddles work partly by turning, but mostly by angling the blade to create hydrodynamic forces. A skilled helmsman could make subtle adjustments, maintaining course or executing precise turns. In rough conditions, steering required strength, endurance, and constant attention. On long voyages, helmsmen rotated in shifts, with the navigator directing course changes based on celestial observations and environmental cues. Provisioning for voyages required careful planning and extensive preparation. Staple foods included preserved breadfruit, which could be fermented into a paste that lasted months, dried fish and squid, coconuts providing both food and drink, and taro or sweet potato that could last several weeks if properly stored. Fresh water was carried in gourds, bamboo sections, or coconut shells, with quantities calculated based on voyage length and crew size. Some voyages collected rainwater using sails or mats to funnel rain into containers, supplementing carried water supplies. Living plants and animals were brought on colonization voyages. Taro corms, breadfruit cuttings, coconut seedlings, and other plant starts had to be kept alive during voyages lasting weeks. This required protecting them from salt spray, providing fresh water, and ensuring they arrived healthy enough to plant. Pigs, chickens, and dogs were brought as domesticated animals, requiring food and water throughout the voyage. The logistics of supporting all this living cargo, while also feeding and housing dozens of human voyagers, was complex, requiring careful planning and resource management. The social organization of voyages reflected the hierarchical nature of Polynesian societies. The navigator held high status with authority over course and sailing decisions. The captain or chief organized the expedition and commanded the crew. Skilled sailors managed sails, steering, and daily operations. Common crew members paddled when wind was insufficient, bailed water, maintained the vessel, and performed other necessary tasks. On colonization voyages, the passenger list included men and women, young and old, representing a cross-section of society capable of establishing a complete new community. The decision to launch an exploration or colonization voyage involved multiple factors. Population pressure on home islands sometimes necessitated finding new lands. Resource depletion, political conflict, or simple desire for adventure-motivated voyages. Religious or cultural factors also played roles, with some voyages undertaken to fulfill prophecies or follow spiritual guidance. Once a decision was made, extensive preparations began, constructing or refitting canoes, gathering provisions, selecting crew and passengers, and waiting for favorable sailing conditions. Timing voyages to coincide with seasonal wind patterns was crucial. The Pacific features trade winds blowing generally from east to west in tropical latitudes, and westerlies blowing west to east in higher latitudes. Navigators understood these patterns and planned voyages to use favorable winds. Sailing eastward against the trades was difficult, but possible by tacking or by sailing to higher or lower latitudes where winds were more favorable. The seasonal reversal of winds in some regions, like the monsoons, provided windows for return voyages that would be difficult or impossible at other times of year. The psychological dimension of voyaging into unknown oceans cannot be overstated. Imagine sailing for days or weeks with no land visible, not knowing if you'll find anything before supplies run out. The faith required to continue when days turn to weeks and still no land appears is extraordinary. Some voyages undoubtedly ended in disaster, with canoes lost at sea, crews dying of thirst or exposure, or survivors reaching land too few and too weak to establish viable populations. For every successful colonization we know about, there were likely multiple failures we'll never know about. Yet they persisted. The discovery of Hawaii, over 2,000 miles from the nearest other Polynesian islands, required either extraordinary luck or deliberate exploration far beyond sight of land. Once discovered, colonizing expeditions had to make the same journey, proving it wasn't a one-time accident. Easter Island, even more remote, required similar dedication. New Zealand, in temperate latitudes far south of tropical Polynesia, required adapting to entirely different environmental conditions. Each of these achievements demonstrated remarkable capabilities. The maintenance of trade and contact between island groups showed that voyaging wasn't just about initial colonization, but about maintaining maritime networks. Archaeological evidence shows that some island groups traded with each other for centuries after initial settlement. Obsidian from one island appears in archaeological sites on islands hundreds of miles away. Pottery styles and other cultural elements spread between islands, requiring ongoing contact. Some oral traditions remember specific voyages between island groups, suggesting that inter-island voyaging was more common than simply a colonization phase followed by isolation. However, isolation eventually occurred in many cases. Hawaii and Easter Island, the most remote Polynesian outposts, lost contact with other Polynesian islands after initial settlement. The distances were too great, the voyages too dangerous, or the knowledge of return routes was lost. These isolated populations developed unique cultures, adapting to their specific environments while maintaining core Polynesian cultural elements. The isolation lasted until European contact, when these distant islands were connected to the wider world again. The impact of Polynesian voyaging on the islands they settled was profound. Pacific islands had evolved in isolation for millions of years, developing unique ecosystems with endemic species found nowhere else. Polynesian arrival brought extinction to many island species, particularly flightless birds that had no defenses against human hunting or introduced predators like rats and dogs. Forests were cleared for agriculture, native plants replaced with introduced crops, and island ecosystems transformed. The environmental impact shows the success of Polynesian colonization, but also its costs. The cultural adaptations Polynesians made to different islands demonstrate remarkable flexibility. In tropical islands, they maintained traditional crops and lifestyles with minor modifications. In New Zealand's temperate climate, where tropical crops struggled or failed, the Maori adapted by focusing on sweet potatoes, which tolerated cooler temperatures, and by developing extensive hunting and foraging traditions, exploiting New Zealand's abundant bird life and marine resources. Despite radical environmental differences, they maintained Polynesian language, social structures, and cultural identity. The voyaging tradition gradually declined after the major phase of expansion ended. By the time Europeans arrived in the Pacific in the 16th century, long-distance voyaging had largely ceased, though inter-island voyaging continued in many areas. The reasons for this decline remain debated. Perhaps all habitable islands had been found, removing the motivation for exploration. Population pressures that drove earlier expansion may have eased. Climatic changes might have made voyaging more dangerous. Or perhaps the knowledge simply gradually eroded as generations passed without undertaking major voyages. The rediscovery of traditional navigation in modern times represents a cultural renaissance. By the mid-20th century, traditional navigation knowledge had nearly disappeared, surviving in only a few locations like the Caroline Islands. The construction of Archaeological and its successful voyage from Hawaii to Tahiti in 1976, using traditional navigation, demonstrated that ancient techniques remained viable. Micronesian navigator Mo Pialat, who guided that voyage, taught Hawaiian crew members, transferring knowledge across cultural boundaries, just as ancient navigators must have done. Since that pioneering voyage, Archaeological and other traditionally built and traditionally navigated canoes have sailed throughout the Pacific and beyond, completing circumnavigations of the Pacific and even voyaging to other oceans. These voyages serve multiple purposes: cultural revitalization, environmental awareness, educational outreach, and continued refinement of traditional techniques. They prove definitively that Polynesian ancestors could have and did accomplish what archaeology and genetics show they did. The crews of these modern voyaging canoes experience what their ancestors experienced: the vast emptiness of the open ocean, the thrill of making landfall after weeks at sea, the physical and mental challenges of long voyages, and the profound connection to ocean, sky, and canoe. Their testimonies provide insights into ancient voyaging that pure scholarship cannot. They understand viscerally what it takes to sail without instruments, to trust in the stars and waves, to push through fear and doubt to reach distant goals. The scientific study of Polynesian navigation has grown increasingly sophisticated. Researchers combine archaeological evidence, linguistic analysis, genetic studies, computer modeling, and experimental voyaging to understand how the expansion occurred. Computer simulations can model drift voyages versus purposeful sailing, testing whether accidental drift could explain observed colonization patterns or whether deliberate exploration is required. The consensus increasingly supports deliberate, planned voyages rather than accidental drift, though some islands may have been initially discovered accidentally before deliberate colonization voyages were organized. The cultural significance of voyaging in Polynesian societies extended beyond mere transportation. Navigators held high status, their knowledge was sacred, and their abilities were sometimes seen as having supernatural elements. Navigation knowledge was power, both practically in enabling voyages and symbolically in connecting navigators to divine or ancestral sources of knowledge. The chance-preserving navigational information were not just mnemonic devices, but sacred texts, connecting practitioners to their ancestors who had first discovered these techniques. The legacy of Polynesian navigation extends far beyond Polynesia. It demonstrates human capabilities that Western science long dismissed as impossible. The idea that people without instruments, charts, or writing could navigate across thousands of miles of ocean seemed absurd to many European scholars, who assumed Polynesian settlement resulted from accidental drift. The vindication of traditional navigation knowledge challenges Western assumptions about what constitutes legitimate knowledge and technology. It shows that sophisticated capabilities can exist without leaving archaeological traces that Western science recognizes. For modern Polynesians, voyaging revival represents cultural identity and pride. After centuries of colonization, Christianization, and Western influence that often deprecated traditional knowledge, the demonstration that ancestors were master mariners, accomplishing feats that still impress, provides cultural validation. Young Polynesians training in traditional navigation connect with their heritage in profound ways, learning not just techniques but philosophies, values, and identities. The voyaging canoes become symbols of cultural survival and resurgence. The Polynesian expansion also offers lessons for our spacefaring future. Voyaging to distant islands across vast oceans with limited resources and uncertain prospects mirrors humanity as future expansion into space. The courage, planning, skills, and cultural systems that enabled Polynesian success may inform how we approach interstellar voyaging centuries hence. Both require accepting enormous risks, trusting in technology and knowledge, and committing to journeys whose success is uncertain, but whose potential rewards justify the attempt. Ultimately, the Polynesian navigators represent humanity at its best: curious, courageous, skilled, and determined. They faced the greatest challenges nature could offer, vast oceans separating tiny islands, and they conquered them. They didn't wait for perfect technology or complete knowledge. They used what they had, refined it through experience, and pushed the boundaries of human achievement. Their story deserves celebration, not just as impressive history, but as inspiration for what humans can accomplish when we combine intelligence, courage, and determination in pursuit of seemingly impossible goals. Chapter 7. Changing Seas. Understanding ancient ocean crossings requires understanding how dramatically different Earth's geography was during the Ice Age. Sea levels, coastlines, weather patterns, and even ocean currents differed significantly from today. These environmental factors made some crossings easier than we might assume, while making others more challenging. Reconstructing Ice Age geography is crucial for understanding how ancient humans spread across the globe. During the last glacial maximum, around 26,000 to 19,000 years ago, sea levels were approximately 400 feet lower than today. Massive ice sheets, up to 2 miles thick, covered much of North America, Northern Europe, and parts of Asia. This ice came from ocean water, so removing it from the sea dropped global sea levels dramatically. The effect was to expose vast areas of continental shelf that are now underwater, fundamentally changing Earth's geography. The Sunda Shelf, the shallow continental shelf of Southeast Asia, was completely exposed during glacial periods. Sumatra, Java, Borneo, and the Malay Peninsula were all connected to mainland Asia, forming a subcontinent called Sundaland, roughly the size of India. Humans could walk from Thailand to Borneo without ever seeing deep water. Similarly, the Sahul Shelf connected Australia, New Guinea, and Tasmania into a single landmass. These exposed shelves transformed what we think of as island hopping into simple overland migration. However, even with maximum glacial conditions, a water barrier remained between Sundaland and Sahul. The Wallacea region, named after naturalist Alfred Russel Wallace, consists of deep trenches and channels created by tectonic activity. These never dried up, even at the lowest sea levels. The biogeographic divide Wallace identified between Asian and Australian fauna exists precisely because these water barriers prevented animal migration, but they didn't stop humans. Somehow, our ancestors crossed these straits, beginning at least 65,000 years ago. The width of these water crossings varied depending on sea level at different times. During maximum glacial conditions, the narrowest crossing was probably around 50 to 60 miles, possibly less depending on the exact route. During interglacial periods or earlier phases of the last ice age when sea levels were higher, the crossings could have been significantly longer. The exact timing of human migration to Sahul affects how difficult the crossing would have been. Earlier migrations faced wider water barriers, but possibly better climate conditions. Ocean currents during the Ice Age differed from today's patterns. Lower sea levels restricted ocean circulation through what are now straits and passages. Changed atmospheric patterns due to extensive ice sheets altered wind patterns, which in turn affected surface currents. These changes could have made some crossings easier by providing favorable currents while making others more difficult. Reconstructing ancient ocean currents is challenging but computer models suggest significant differences from modern patterns. Weather patterns were also different. The Ice Age wasn't uniformly cold. It featured complex climate variations with warm and cold phases, wet and dry periods, and significant regional variation. Some regions experienced more rainfall, others more drought. Storm patterns differed from today's. These changes affected sailing conditions. Favorable wind patterns might have made certain crossings easier at specific times. The challenge is that we have limited evidence for Ice Age weather patterns, making it difficult to know what conditions ancient mariners faced. Sea surface temperatures were cooler during glacial periods, affecting evaporation rates and thus cloud formation and rainfall. Cooler oceans might have meant fewer storms, but also less rain for collecting water during voyages. The exact effects on maritime conditions remain uncertain, but they were certainly different from today. Ancient mariners adapted to the conditions they experienced, which may have been either more or less favorable than modern conditions depending on specific routes and timing. The exposed continental shelves weren't empty wastelands. They included river valleys, lakes, coastal plains, and likely supported substantial plant and animal life. Some of the most attractive and densely populated land areas of Ice Age Southeast Asia are now underwater. Archaeological evidence for human activity in these regions is lost beneath hundreds of feet of ocean. We're literally missing significant portions of human prehistory because the lands where people lived are now submerged. This lost landscape affects our understanding of maritime capabilities. Coastal settlements that might have shown boat-building activities, harbors, or other maritime infrastructure are underwater and largely inaccessible. The oldest coastal sites we can study are those that were well inland during the Ice Age and thus escaped submersion. This creates a massive sampling bias in archaeological evidence. We're studying only the margins of Ice Age human geography, not the centers. Rising sea levels at the end of the Ice Age, beginning around 18,000 years ago, dramatically changed geography. Coastlines retreated rapidly in geological terms, sometimes hundreds of yards per human lifetime. Entire river valleys flooded, becoming bays and straits. Low-lying plains disappeared beneath advancing seas. This must have been traumatic for coastal populations, forcing constant retreat and adaptation. Flood myths from cultures worldwide might preserve memories of these dramatic sea level changes. The flooding created new islands and made some crossings more difficult. Islands that were once part of continents became isolated. This could strand populations that had walked to what became islands, forcing them to develop or maintain maritime capabilities to maintain contact with other populations. Conversely, some islands that existed during low sea levels were completely submerged, possibly along with any human populations living there. We'll never know about these lost islands and their inhabitants. Climate changes also affected the resources available for boat building. Forest composition changed dramatically between glacial and interglacial periods. Some timber species that might have been ideal for boat construction were more or less available depending on climate. The same applies to reeds, vines for cordage, and resins for waterproofing. Ancient peoples had to use whatever materials their local environment provided, which varied over time as climate changed. Modern sea level rise, though concerning for current populations, is much slower than the most rapid post-glacial rises. Between 15,000 and 8,000 years ago, sea levels rose over 300 feet, an average of about 1 foot per generation, but with periods of much more rapid rise. Coastal populations experienced constant change, requiring adaptability and likely encouraging maritime capabilities as a survival strategy. Being good with boats became essential when your homeland kept disappearing underwater. Understanding Ice Age geography transforms our perspective on ancient ocean crossings. What seems impossible with modern geography becomes more understandable in its proper context. The crossings were still challenging and dangerous, requiring skill, courage, and technology. But they weren't quite as extreme as modern maps suggest. Ancient humans were bold and capable, but they weren't superhuman. They succeeded because they were skilled and because geography was different than we often assume. The transformation of Earth's coastlines over the past 100,000 years represents one of the most dramatic environmental changes our planet has experienced. These changes directly affected human migration patterns, settlement locations, and the development of maritime capabilities. To truly understand how ancient humans crossed oceans, we must understand how radically different those oceans were from what we see today. The story of rising and falling seas is intimately connected to the story of human expansion across the globe. The mechanism driving these changes was glaciation. During cold periods, water evaporates from oceans and falls as snow on polar regions and high mountains. Instead of melting and returning to the sea, this snow accumulates year after year, compressing into ice sheets. The Laurentide ice sheet covered most of Canada and the northern United States, reaching thicknesses of over 2 miles in places. Similar ice sheets covered Scandinavia and parts of Siberia. Smaller glaciers expanded dramatically in mountain ranges worldwide. All of this ice came from ocean water, and removing it dropped global sea levels by astonishing amounts. The last glacial maximum, the coldest point of the most recent ice age around 26,000 to 19,000 years ago, saw sea levels approximately 390 to 430 feet lower than today. To put this in perspective, imagine the ocean dropping the height of a 40-story building. Vast areas of continental shelf, now underwater, became dry land. The English Channel was a river valley. The Persian Gulf was a plain with rivers running through it. The seafloor between Siberia and Alaska formed the Bering Land Bridge, allowing animals and humans to walk between continents. But sea level changes weren't uniform or gradual. They fluctuated dramatically based on global temperature variations. Within the last glacial period, there were warmer interstadial periods when ice melted and sea levels rose partially, followed by stadial periods when ice sheets expanded again and sea levels dropped. These fluctuations happened over centuries to millennia, fast enough that coastal human populations would have noticed significant changes within lifetimes. A beach camp established in youth might be miles inland by old age, or conversely, flooded by advancing seas. The exposed continental shelves weren't barren ocean floor. They featured diverse landscapes, river valleys, lakes, forests, grasslands, and coastlines. These were often prime territories, with access to both terrestrial and marine resources. Rivers that now end at modern coastlines once flowed many miles further, creating extensive river valleys and deltas on the exposed shelf. These valleys attracted human settlement, offering fresh water, fertile soils, and abundant game. Unfortunately, all evidence of human activity in these areas is now underwater, lost to rising post-glacial seas. Sundaland, the exposed Sunda shelf of Southeast Asia, was enormous, roughly the size of modern India. During glacial maxima, you could walk from Malaysia to Borneo, Java, and Sumatra without crossing water. This vast region supported tropical rainforests in wetter areas and savanna in drier regions. Archaeological and genetic evidence suggests it was densely populated by humans during the Ice Age. It may have been a crucial homeland for Southeast Asian populations, a center from which people expanded in multiple directions. Then, as seas rose after the glacial maximum, Sundaland drowned, forcing populations to retreat to higher ground that became the modern islands. The flooding of Sundaland had profound effects on human populations. As sea levels rose, people were forced to relocate constantly. Settlements established on the coast would find the ocean creeping closer year by year. Eventually, they'd have to move inland, abandoning their homes to the sea. This process repeated generation after generation as seas rose over 300 feet over the course of about 10,000 years. The most rapid rises during periods of catastrophic ice sheet collapse could see sea levels jump several feet in a single generation, flooding vast low-lying areas. Some researchers believe that flood myths from cultures worldwide preserve memories of these dramatic sea level rises. The biblical flood, the Mesopotamian flood narrative in the Epic of Gilgamesh, Aboriginal Australian flood stories, Native American flood myths, all might contain distorted memories of real catastrophic flooding as Ice Age seas rose. While a literal global flood covering all mountains never occurred, regional catastrophes definitely did. The Black Sea, for instance, was a freshwater lake during the glacial period. Around 5600 BCE, rising Mediterranean waters breached the Bosporus, flooding into the Black Sea basin. Water poured through this breach like a massive waterfall, raising the Black Sea level by hundreds of feet and flooding extensive coastal settlements. People living around the lake would have witnessed an apocalyptic flood, exactly as regional myths describe. The Bering Land Bridge, connecting Asia and North America, opened and closed multiple times during glacial cycles. During glacial maxima, when sea levels dropped, the Bering Strait became land, allowing animals and humans to walk between continents. Current consensus suggests that humans first crossed into the Americas around 15,000 years ago or slightly earlier, though some controversial evidence suggests earlier dates. The land bridge wasn't a narrow strip. At its maximum extent, it was over 1,000 miles wide from north to south, a vast Arctic grassland supporting mammoths, bison, horses, and other megafauna. Humans following these animals gradually moved eastward, eventually entering the Americas. The closure of the Bering Land Bridge, as seas rose after the glacial maximum, isolated American populations from Asia. For thousands of years, the only contact would have been by boat along the northern Pacific coast. This isolation allowed American populations to develop distinctive cultures, languages, and genetic characteristics. When Europeans arrived in the 15th century, they encountered peoples who had been separated from the Old World for over 10,000 years, evolving independently during that entire period. The Mediterranean Sea experienced dramatic changes during glacial periods. Sea levels dropped so much that many islands grew significantly larger and closer together. Sicily almost connected to mainland Italy. Corsica and Sardinia merged into a single large island. The distance between islands decreased substantially, making island hopping easier. However, some straits remained even at lowest sea levels, particularly the Strait of Gibraltar, which maintained the Mediterranean's connection to the Atlantic. The Mediterranean never completely dried up during the glacial period, though it had done so earlier in Earth's history during the Messinian salinity crisis about 5 million years ago. The Persian Gulf provides one of the most dramatic examples of sea level impact. During glacial maxima, the Gulf was completely dry, a river valley where the Tigris and Euphrates rivers joined and flowed across the exposed Gulf floor before emptying into the Indian Ocean hundreds of miles south of the modern coastline. This river valley was likely fertile and well-watered, potentially supporting significant human populations. As seas rose after the glacial maximum, the Gulf flooded relatively rapidly, with the entire basin filling over the course of a few thousand years. Any human settlements in the Gulf basin were drowned, and populations were forced to retreat to the surrounding higher ground that now forms the modern coastline. Some researchers speculate that the flooding of the Persian Gulf might be connected to Mesopotamian flood myths and possibly even the Garden of Eden story. The Gulf region during the glacial period would have been an attractive environment, a well-watered river valley surrounded by increasingly arid lands. If human populations lived there and were then forced out by rising seas, the memory might have transformed into myths about a lost paradise. This remains speculative, but it illustrates how environmental changes might influence mythology and cultural memory. Ocean temperatures during glacial periods were significantly cooler than today, by perhaps 5 to 10 degrees Fahrenheit in many regions. Cooler water affects marine ecosystems dramatically. Some fish species shifted their ranges toward the equator, while cold-adapted species expanded further from polar regions. Whale migration routes changed. Seal populations redistributed. For human populations dependent on marine resources, these changes required adaptation. Fishing techniques effective for one species might not work for the species that replaced it. Traditional fishing grounds might become less productive or support different species than previous generations had known. The cooling also affected weather patterns. With more ice coverage reflecting sunlight and colder oceans, global atmospheric circulation changed. The jet stream shifted position. Storm tracks moved. Rainfall patterns altered dramatically in many regions. Some areas that are now deserts received more rainfall during glacial periods, while some currently wet regions became drier. These changes affected not just where humans could live, but also what resources were available for boat building. The distribution of forests changed, affecting the availability of suitable timber. Reed beds expanded or contracted based on local water availability. Wind patterns differed from modern conditions, with implications for sailing. The trade winds and westerlies, the major wind systems that drive ocean circulation and have been crucial for historical maritime trade and exploration, had different strengths and positions during glacial periods. Some sailing routes that are favorable today might have been difficult during the Ice Age, while routes that are challenging now might have been easier. Without detailed atmospheric reconstructions, we can't know exactly what conditions ancient mariners faced, but we know they were different from today's conditions. Ocean currents were also altered by glacial conditions. The Great Ocean Conveyor Belt, the global thermaline circulation that moves water between basins, operated differently when ice sheets affected water temperature and salinity. Surface currents, driven by winds, changed as wind patterns changed. These current alterations affected which sailing routes were feasible and what speeds could be achieved. Some island groups might have been easier to reach during glacial periods due to favorable currents, while others became more challenging. The biological productivity of oceans changed with temperature and circulation patterns. Cold waters generally contain more dissolved oxygen and support more nutrients, leading to higher productivity in many regions. During glacial periods, some areas of ocean that are relatively unproductive today supported abundant marine life. Conversely, some currently productive regions might have been less so. These changes affected where fish congregated, where marine mammals fed, and consequently where human populations could most successfully exploit marine resources. Sea ice extent was dramatically greater during glacial periods. The Arctic ice cap extended much further south, while Antarctic ice shelves expanded far beyond their current extent. This ice created barriers to navigation in high latitudes, but also created new opportunities. Some Arctic peoples learned to hunt on sea ice, developing sophisticated adaptations for ice edge hunting. The ice also created highways of sorts. During winter, frozen seas could be traversed on foot or by sled, allowing movement between islands or coastal areas that were separated by open water during summer. The transition from glacial maximum to modern conditions, the period from about 19,000 years ago to roughly 7,000 years ago, saw the most dramatic environmental changes. Sea levels rose irregularly, with periods of slow rise interrupted by rapid jumps when ice sheets collapsed. The most dramatic event was Meltwater Pulse 1A, around 14,000 years ago, when sea levels jumped approximately 50 feet in less than 500 years, possibly in as little as a century. This catastrophic rise would have flooded vast coastal areas, displaced huge human populations, and fundamentally reshaped human geography. Different regions experienced sea level rise differently. Areas that had been depressed by the weight of ice sheets, like Scandinavia and Canada, actually rose relative to sea level as the ice melted and the land rebounded isostatically. These regions experienced less dramatic flooding or even net land gain despite rising global sea levels. Conversely, regions far from ice sheets, like Southeast Asia, experienced the full effect of rising seas with no compensating land rise. This differential response means that sea level history varies by location. There's no single global curve that applies everywhere. The rate of sea level rise varied considerably over time. The fastest rises occurred during periods when ice sheets collapsed. When massive ice shelves or the edges of ice sheets broke off and floated away, sea level could rise very rapidly. The Laurentide ice sheet, covering North America, had several major collapse events. Each time a large section broke away, sea level jumped globally within decades. These rapid rises would have been catastrophic for coastal populations, giving them little time to adapt or relocate. Entire regions would flood in a human lifetime, forcing mass migrations. Some researchers have proposed that rapid sea level rises might have actually encouraged maritime development. As seas rose and flooded coastal plains, populations were forced to either retreat inland or adapt to living in increasingly watery landscapes. Those who chose adaptation would have needed boats for transportation, fishing, and maintaining contact with increasingly isolated settlements. The pressure of rising seas might have driven innovation in boat building and navigation. Communities that developed superior maritime technology would have had survival advantages, leading to selection for seafaring cultures. The flooding also created new islands and changed the configuration of existing ones. During the glacial period, many current islands were hilltops in continuous landscapes. As seas rose, valleys flooded, isolating these hills and creating islands. Some islands that existed during low sea levels were completely submerged as seas rose. The map of islands available for colonization changed continuously over thousands of years. An island chain that offered stepping stones across an ocean during one period might be partially submerged and more difficult to traverse later. Estuaries and river mouths migrated continuously as sea levels changed. During low sea levels, rivers cut deep valleys across the exposed continental shelf. As seas rose, these valleys flooded, creating extensive estuaries. These estuaries were ecologically rich environments, mixing fresh and salt water, supporting abundant shellfish, fish, and birds. They attracted human settlement, but they also kept changing position as seas rose. A settlement established at a river mouth might find that mouth moving upstream as the sea advanced, eventually becoming an inland site far from the coast. Coral reefs, crucial to many Pacific island ecosystems, had to constantly adapt to changing sea levels. Reefs grow upward towards sunlight, so as sea levels rose, they grew upward too. But the rate of reef growth had to match the rate of sea level rise, or reefs would drown in water too deep for corals. Some reefs successfully tracked rising sea levels, while others drowned. The distribution of reefs changed over time, affecting which islands had protected lagoons and which were exposed to open ocean. This influenced which islands were easier to approach and settle. The modern stabilization of sea levels, occurring roughly 7,000 years ago, fundamentally changed human possibilities. For the first time in thousands of years, coastlines stopped moving. Settlements could be established on the coast without fear of flooding. Harbor works became worthwhile investments since they wouldn't be submerged or left high and dry within generations. Fishing grounds remained in consistent locations. This stability allowed the development of more sophisticated coastal and maritime cultures. The great maritime civilizations of the Bronze Age, the Minoans, Phoenicians, and others, only became possible after sea levels stabilized. Understanding these environmental changes is crucial for interpreting archaeological evidence of early seafaring. Sites that are now inland might have been coastal during periods of lower sea levels. Conversely, the most important sites, Those right on the ancient coastlines where maritime activities would have been concentrated are now underwater. We're forced to study ancient maritime cultures from their hinterlands, missing the coastal core where boat building, fishing, and ocean voyaging originated. This creates a fundamental bias in the archaeological record that we must account for when reconstructing ancient maritime capabilities. Climate models and paleoenvironmental reconstructions continue improving, giving us increasingly detailed pictures of Ice Age conditions. By combining geological evidence, ice cores, ocean sediment cores, and computer modeling, researchers can estimate temperature, rainfall, vegetation, and even wind patterns for different periods. This information helps us understand what conditions ancient mariners faced, what resources they had available, and what challenges they overcame. Each improvement in our understanding of ancient environments enhances our understanding of ancient human achievements. The lesson from studying these environmental changes is that Earth's geography is not fixed. Coastlines move, islands appear and disappear, climate changes, and human populations must adapt or perish. Our ancestors lived through dramatic environmental changes that would be catastrophic for modern civilization with its fixed infrastructure and stable borders. Yet they not only survived but thrived, developing new technologies and spreading to new territories. The resilience and adaptability demonstrated by ancient humans facing rising seas and changing climates offers both inspiration and lessons for modern humans facing our own period of environmental change. Chapter 8. Archaeological revelations. Archaeological evidence for ancient maritime activities comes from multiple sources, each providing pieces of a puzzle that reveals our ancestors' seafaring capabilities. While boats themselves rarely preserve, indirect evidence tells the story. Shell middens, obsidian trade networks, fish remains in ancient sites, and island populations all point to sophisticated maritime adaptations going back tens of thousands of years. Modern archaeological techniques continue revealing new evidence, pushing back dates for various maritime achievements and forcing revisions to long-held assumptions. Shell middens, huge deposits of discarded shells from consumed shellfish, appear in coastal sites worldwide. Some date back over 100,000 years, proving that ancient humans regularly exploited marine resources. The shells themselves provide information about seasonal occupation, as different species are available at different times of year. Some middens contain shells from deep water species that couldn't be gathered by wading or diving from shore, suggesting boat use for harvesting. The sheer size of some middens indicates intensive marine resource exploitation over extended periods. Obsidian, volcanic glass prized for making sharp tools, appears in archaeological sites far from any volcanic source. Chemical analysis can identify the specific volcano where obsidian originated, allowing researchers to trace trade networks. Obsidian from the island of Melis appears in mainland Greek sites over 9,000 years ago, proving that boats crossed the Aegean Sea to obtain this valuable material. Similar patterns appear worldwide. Islands with desirable stone resources were visited by ancient peoples who could only have arrived by boat. Fish remains in archaeological sites provide direct evidence of fishing activities and, by inference, boats. Some sites contain bones from deep-water fish species that can only be caught offshore, requiring boats to reach. The variety of fish species sometimes indicates sophisticated fishing techniques, including hooks, nets, and traps. At Jaramalai Cave in East Timor, fish remains over 40,000 years old include tuna and other pelagic species requiring open ocean fishing, suggesting both boats and considerable seafaring skill. Isotope analysis of human remains reveals diet, including the proportion of marine versus terrestrial foods. Coastal populations often show high marine diet signatures, confirming that seafood was a dietary staple. Some inland populations show surprising marine signatures, suggesting trade in dried fish or seasonal trips to coast. These chemical analyses provide information that skeletal remains alone cannot reveal, building a picture of how ancient peoples exploited marine resources. Underwater archaeology is revealing submerged sites from when sea levels were lower. In the Mediterranean, the Black Sea, and off Southeast Asian coasts, researchers find ancient settlements now underwater. These sites are difficult to excavate and preserve, but they provide crucial evidence for Ice Age coastal adaptations. Some preserve organic materials better than land sites due to anoxic underwater conditions. Each discovery potentially rewrites what we know about ancient coastal populations and their maritime capabilities. Rock art depicting boats appears in various locations worldwide. Scandinavian rock carvings show boats with multiple paddlers dating to around 10,000 years ago. Egyptian rock art shows boats with sails. Aboriginal Australian rock art includes paintings of boats that might represent either indigenous watercraft or European vessels seen after contact. Dating rock art is challenging, but where reliable dates exist, they push evidence for boat use back thousands of years. Experimental archaeology tests theories about ancient maritime capabilities. Researchers build replicas of ancient boat types using only period-appropriate materials and techniques, then test them in actual sailing conditions. These experiments demonstrate what was possible with ancient technology. The Kon-Tiki expedition, Ra expeditions, and various Polynesian voyaging canoe reconstructions all proved that traditional boat designs and navigation techniques were fully capable of accomplishing the journeys ancient peoples made. Genetic studies complement archaeological evidence. When genetics shows human presence on an island at a particular time, but archaeology has found no contemporary sites, researchers know where to look. DNA indicates the timing and scale of population movements, helping archaeologists understand migration patterns. Ancient DNA from skeletal remains directly demonstrates who lived where and when, sometimes confirming and sometimes contradicting archaeological interpretations. Computer modeling helps researchers understand ancient seafaring. By inputting data on currents, winds, wheel levels, and boat performance characteristics, researchers can model possible routes ancient mariners might have taken. These simulations identify which routes were feasible, which were impossible, and which required specific conditions or technologies. While models can't prove what actually happened, they help narrow possibilities and test hypotheses. Ethnographic studies of recent traditional maritime cultures provide analogies for ancient practices. By studying how traditional navigators in the Caroline Islands, how Aboriginal Australians constructed bark canoes, or how Inuit built kayaks, researchers gain insights into possible ancient techniques. These aren't perfect analogies. Modern traditional cultures aren't unchanged survivals from prehistory, but they demonstrate what's possible with pre-industrial technology and provide hypotheses to test. Recent discoveries continue surprising researchers. Stone tools on Crete dated to 130,000 years ago proved that someone, possibly Neanderthals or other hominins, crossed significant water to reach the island far earlier than previously thought possible. Each new discovery pushes maritime capabilities further back in time. Human remains in the Philippines dated to over 60,000 years old, evidence of sophisticated tool use, and hunting on remote Pacific islands all challenge previous assumptions about what ancient peoples could accomplish. The pattern is clear. Whenever researchers seriously investigate, they find evidence of earlier and more sophisticated maritime activities than previously assumed. The absence of boat remains shouldn't be interpreted as absence of boats. The archaeological record is incomplete, biased toward preservation of stone and bone while organic materials disappear. Ancient peoples were far more capable than we've given them credit for. They explored, they adapted, they innovated, and they succeeded in colonizing virtually every habitable place on Earth, regardless of water barriers. So how did the first humans cross oceans without boats? The simple answer is, They didn't. They did have boats. They just weren't the kind of boats that are preserved in the archaeological record. Simple rafts of lashed logs, reed boats bound with plant fibers, dugout canoes burned and scraped from single trees. Bark canoes, skin boats, all were fully capable watercraft that left virtually no archaeological trace. The question isn't how they crossed oceans without boats, but how they built boats, navigated, and mustered the courage to venture into the unknown. The evidence is overwhelming. Humans reached Australia at least 65,000 years ago, crossing significant stretches of open ocean. They colonized islands throughout Southeast Asia even earlier. They reached Madagascar from Indonesia 4,000 years ago. They settled every Pacific island over a period of thousands of years. These accomplishments required boats, navigation skills, and organized expeditions. They weren't accidents. They were achievements of capable, intelligent people who developed sophisticated maritime adaptations. What we've learned transforms our understanding of human prehistory. Our ancestors weren't just land-dwelling hunters and gatherers who occasionally stumbled upon water. Many populations developed deep maritime adaptations, building their cultures around the sea. They fished, gathered shellfish, and hunted marine mammals. They built boats and became skilled sailors. They passed maritime knowledge through generations, creating seafaring traditions that lasted thousands of years. The technology was simpler than modern vessels, but entirely adequate for the task. You don't need steel hulls and diesel engines to cross oceans. You need watercraft that float and can be controlled, provisions for the journey, and knowledge of navigation. All of these were within ancient capabilities. The ingenuity required was substantial, but not beyond human capacity. Our ancestors were as intelligent as we are, just working with different materials and knowledge bases. Navigation without instruments seems impossible to modern people, dependent on GPS and electronic charts. But traditional navigators demonstrated that human senses and memory are sufficient. Star positions, wave patterns, bird behavior, cloud formations all provide navigation information. The challenge isn't perceiving these cues, but learning to interpret them correctly. This requires training and experience, but cultures that valued navigation knowledge could pass it down through generations, maintaining sophisticated wayfinding traditions. The courage required shouldn't be underestimated. Setting off across open ocean, possibly with your entire family, with no guarantee of finding land, facing storms, thirst, and the constant possibility of death, this takes remarkable bravery. Yet humans repeatedly made these journeys. Some failed, boats lost at sea with all hands. But enough succeeded to populate islands across the Pacific, Indian, and Atlantic Oceans. The human spirit of exploration and adventure is ancient and deep. What motivated these journeys? Certainly practical concerns, population pressure, resource depletion, conflict, but also curiosity, the desire to know what lies beyond the horizon. Humans are naturally exploratory. We see a distant island or the edge of the world and wonder what's there. This curiosity drove us out of Africa, across Eurasia, and eventually to every continent and virtually every island. The same impulse that sent ancient mariners across unknown oceans sends modern humans into space. The environmental context mattered. Ice Age geography was different, with lower sea levels exposing land bridges and reducing some water crossings. But significant barriers remained, and humans crossed them. Climate changes forced adaptations, including maritime ones. Rising sea levels at the Ice Age's end pushed coastal populations to develop better boats and navigation, or lose their homelands to the advancing ocean. The loss of evidence frustrates attempts to fully understand ancient maritime capabilities. The boats are gone, the harbors submerged, the navigation schools unwritten. We're reconstructing this history from fragmentary evidence, genetic markers, shell middens, obsidian trade, and the undeniable presence of humans on islands they could only reach by sea. is like reconstructing a vehicle from tire tracks. We know something passed this way. We can infer some characteristics, but we can't see the vehicle itself. Modern humans inherited this maritime legacy. We're descended from people who crossed oceans, who weren't stopped by water barriers, who kept exploring until they'd reached every habitable place. This achievement rivals any in human history. It required technology, skill, organization, and courage. It demonstrated human adaptability and problem solving. And it was accomplished not once but repeatedly by cultures around the world, each developing their own maritime traditions. The story of how humans crossed oceans is ultimately a story about human capability and determination. Given motivation, we solve problems. Faced with water barriers, we build boats. Uncertain about navigation, we observe, learn, and develop wayfinding systems. Frightened of the unknown ocean, we muster courage and venture forth anyway. These traits, inventiveness, adaptability, and bravery, carried our species from African origins to global dominance. The first human to cross open ocean, standing in a simple boat, looking back at the receding coast, couldn't have imagined the consequences of that journey. They were just trying to reach the island visible on the horizon, to find new resources, to escape enemies, to satisfy curiosity. But that crossing was a pivotal moment in human history. It proved that oceans weren't barriers but highways, that islands weren't unreachable but destinations, that humanity's expansion would continue until we claimed every habitable place on Earth. From that first crossing to Polynesian navigators reaching Easter Island to modern humans exploring space, we remain a species that refuses to be contained, that crosses barriers, that explores beyond the known. The ocean couldn't stop us. Nothing can.